Today I'm going to talk about our research on the mobile security. The topic is anti-plugin. Don't let your app play as an Android plugin. This is a joint work with my colleagues, Cong, Zheng, and Zheng. We are all working at the Palo Networks. Before the presentation, I just want to introduce a little bit about myself. So this is the second time I present at the Black Hat. This it's my pleasure to share our research with the security communities in this platform. And currently, I'm a principal security researcher at Palo Networks. And my research field include mobile security, like discover new malware, and to find out the security issues in the Android system, as well as the web security part. We build a state-of-the-art exploit detection tools, and also we do some fuzzing kind of things to explore the browsers like Safari and IE. And in this presentation, I will show you that how amazing technology called Android plugin technology, and how this technology has been abused by malware to power up the attackers tool. And I will start with some background information about the plugin technology. I think not everyone is familiar with that. And then I will discuss this in detail, like how to design this and how to implement this in order for you to understand why the attacker is so interested in this in this technology. After that, I will show you some statistics and some samples to illustrate how this technology has been abused by malware. And the last is our solution. We try to play against this new type of attack. So first, although plugin technology has been widely used by Android apps, I think not everyone is familiar with this. I will start with some background information with the first question: why plugin technology is quite popular? The Android plugin technology is popular because it was introduced to meet the huge demands of mobile users. I think most of people here and also the normal users will have multiple accounts for your social media apps such as Facebook, Twitter, or WeChat, and like one for personal and one for business. But however, most of the social media apps only allows users to log in one account at the same time. If you want to log in multiple accounts, you have to log out one first and log in another, which is so inconvenience. So also in Android system, user can only launch one instance of an app at the same time, so that there's no way for users to bypass this restriction that's applied by this system. So some developers come up with an idea to call the plugin technology, with which people can launch multiple instances of the same app on the same device, so that users can log in multiple accounts at the same time. So what is the Android plugin technology actually? It's a mechanism to launch an APK file from the file system without installing it in an unrooted device. So we named the Android app to launch as a host app, and name the APK file on the file system as a plugin. So typically, users install the host app first on their device, and they open the host app and use the host app to choose the APK file on the file system, like the one on the SD card, and then they can use the host app to load and launch this plugin APK file dynamically without any installation. Then they can just log in multiple accounts. So this sounds similar to a technique called the DCL, the dynamic code loading, which is a technique allows an app to load and execute code that is not part of initial static database, the code base at runtime. Both of them are used to run additional piece of code that is not presented in the original app package at installation time. But DCL can only load and execute a small piece of code, which is highly integrated to the current app's context. But the plugin technology is more advanced since it can launch a whole APK file. It can launch any APK file as a whole package and contain the code to perform more complicated functionalities and more interactions with the system. So I will show you this in the rest of the presentation. The most popular app that's powered by plugin technology is called the Parallel Space. This app has been downloaded and installed through Google Play for more than 10 million times, and it's quite popular. Basically, this app just leverages plugin technology to run multiple instances of an app that's already installed on user's device. So to use the Parallel Space, user will open this app first and see a panel like this, and then they choose icon that's for which represent the APK file that already been installed. And so, for example, if they choose a Twitter app through this panel, they can launch the Twitter APK file in the Parallel Space, like multiple Twitter instances, so that they can log in multiple accounts simultaneously. Some developers build the library or SDK that implement plugin technology. So any Android app can import their library to gain the power to launch the APK file without installation and launch multiple instances of an app. The most popular one we found is called a Joint plugin, which is developed by Qihoo. They open source the SDK on the GitHub. From then on, it has been imported by many of our apps already. In our research, we will use Joint plugin as an example to explain how plugin technology works and how it has been abused. So from what I just explained, you may have a basic idea that why people want to use plugin technology and who want to use it, especially for the people who want to log in multiple social media accounts at the same time. So now I will use Joint plugin as an example to discuss how they design and implement such amazing technology. So this figure here shows the high-level picture of how Joint plugin works. It involves three major parts: the Android framework, the host app with the Joint plugin SDK, and the plugin apps as each individual APK file on the file system. So the key part of the whole system is a component called a proxy hook, which is located between the plugin file and the system. So it will intercept all of the invocation of a certain Android APIs from the plugin app, as well as the data returned from the framework back to the plugin. So those intercepted invocations will be modified by the Joint plugin, such as changing the parameters and also changing the return value before it's sending to the actual target. And this is the magic for Joint plugin to create a virtual environment on the top of the Android framework within the host app. This is because those interception and the modification is transparent to both plugin and the Android framework. So from the system perspective, it only notice there is a host app is running, and they did not aware of any plugin file, so that those virtual environment can bypass the system restriction, and that is the reason why the host app can leverage plugin technology to launch multiple instances of the same app on the same device. So Joint plugin creates the virtual environment by playing the mind-the-middle game between the plugin and the framework. So hooking mechanism is the pretty straightforward way to achieve this goal. So when we talk about the design of a hooking system, we are actually asking two questions. So how to hook APIs in Android system, and what API to hook in Android system in order to create this virtual environment. The first question is easy to answer because hooking an API in Java is pretty standard. So Java provides the dynamic proxy API for creating a proxy of a class or instances. Some of the APIs are hidden inside the Android framework so that we cannot access them directly. So joint plugin have to rely on the reflection mechanism in order to access them and hook those APIs. The second question, what APIs need to hook in order to create this virtual environment? This is complicated to answer and involving the knowledge of how Android framework works. I will put more time to discuss this, and this is the core part to understand this presentation. So basically, the joint plugin need to hook the APIs in order to perform the following tasks. They have to hook the APIs to load and launch the APK file without installation. And also it can managing the lifecycle of app components. Also need to provide the inter-plugin communication and the plugin management. So, but due to the time limitation of this presentation, I will only focus on the first two tasks. That's to explain how to hook APIs in Android to implement the plugin technology. So first one is how to launch an APK file without installing it. So normally in Android system, the APK or DAX file are loaded by class loader. Once loaded, the class loader will save all of the past DAX file in a list called a DAX element. So whenever the class loader needs to load a class, it will try to find the class by scanning through this list using the class name. So if cannot find it in the current class loader, it will trace back to the parent class loader until the class is founded. Originally, a system will go to a specific path. Usually it's a data app folder to find the installed app's APK file and the related resources. Since the plugin APK has never been installed, so the APK file is now in this folder. So at the moment the user launches the host app, only the host app's APK file has been loaded into the class loader. So at this time, if we try to launch or access a class defined in the plugin's APK file, it will fail to locate this class because the APK file and the class is not in this list. So joint plugin have to hook the class loader in order to find a way to load the plugin APK file from somewhere in the file system and pass it and put the passed file into this list. After this step, if we want to say start activity defined in the plugin APK file, now we can find a class because the mechanism the system will use the mechanism to find that class in this modified list. If you are familiar with the hot patching technique used in Android, they have shared a similar trick. So we know how the joint plugin hook the class loader to launch an APK file without installation, but this is only the first step. The second step for joint plugin is to maintain the lifecycle of app components used in plugin APK file. App components such as activity, service, broadcast receiver, and content provider, they are the basic essential functionalities of mobile app. Unlike the UI component, such as button or text field, the app components are special because their lifecycle is maintained by the system, which means that For the plugin app, it needs to communicate with more frequently with the system if they use the app components. And those communications are the challenging part to create this perfect virtual environment. I will use starting a new activity as an example to show you why the joint plugin need to hook some API to make it work. So if you are already familiar with the Android system, this figure, you should also familiar with this figure. This here shows the whole flow in Android system to start a new activity. So the Android system, the Android app cannot create a new activity by itself. In order to do it, it have to rely on a system service called the Activity Manager Service, or the AMS, which provided by the system, and all the lifecycle management of the components, like the activity, should be performed in this service. So the first step is for the current activity is to invoke the function start activity to notify the AMS to let AMS create a new activity for it. Then the AMS will take over the control and perform a series of tasks like post current activity if needed to create a new activity environment, and also manage the life cycle of each activity in a stack. So after those steps, the AMS will return the control back to the new activity, which is the targeted activity, and then it will invoke a callback function to actually load the plugin's activity class and execute it. And that is the high-level picture of how the Android system creates a new activity. But for our case, to explain the joint plugin, we do not need all of those details. We only need to focus on the following three steps: start activity, create a new activity, and the callback function to to execute the new activity code. So I simplify the previous figure to only leave these three parts to make it clear, and we only focus on the intent sending between the activity and the AMS. So the current activity will invoke the start activity function, which actually sending an intent to the AMS, and the content of the intent is the class of the plugin activity that we want to create it. And so this intent will also be forwarded to the new activity thread, where the callback function handle launch activity will pass this intent and extract a class from the intent, and at this place, this callback function will execute the code of that class. Okay, that is the detail of how the current activity notify the AMS what is the new activity to be created. However, if we want to start an activity defined in the plugin APK file, which has never been installed, it will cause a failure in the AMS. This is because the plugin activity is not defined in the host app's manifest file. Remember that the Android system only aware of the host app. So for each activity to launch it or to use it, we have to define this in the manifest file. But clearly, the system will fail to find the definition in the host app's manifest file. But right now, the joint plugin, so we cannot put the name of each plugin activities to the host manifest file, because the plugin technology is generic. People can launch any APK file as a plugin. So when you create the host app, it's hard to predict what kind of APK file will be launched. So it's no way to copy the manifest file of the plugin APK file to the host app. And so the solution come up with by the join plugin is to predefine some stub components, such as stub activity for every host app. Later on, the join plugin will intercept the intent sending to the AMS to modify it by wrapping it around another intent and put the stub activity class in the intent and forward this intent to the AMS. At this time, there will be no failure because the stub activity class is already defined in the host manifest file. So that's a way that the join plugin for the AMS to start activity that is never defined in the manifest file. And also, we also need to find a place to unwrap this modified intent, because remember that the callback function will extract the class from the intent. If we do not unwrap it, it will extract the stub activity class instead of the plugin's activity. So that is the whole flow to hook the AMS in order to start a new activity. So the place to intercept those intent is in the start activity. Basically, the start activity will get intent, get a bundle of AMS first, and use this bundle to send the AMS. So join plugin just need to hook this specific bundle in the activity, and they can have a chance to intercept all of the invocation. The similar thing to start to hook the AMS to start a new service. So as we just explained, so the Android plugin technology only been introduced less than 2 years. It has been widely used among Android apps, both benign and malicious. And so we use the join plugin library as an example. We searched our internal join plugin, internal APK database. We found around more than 120,000 apps that use join plugin SDK or a customized version of it. But only a little bit more than 5,000 of them are benign. The majority of them are malicious. And we also look into why we market it as malicious, because our dynamic analyzer module detects some malicious behavior from those samples. And we also measure the trend of new malware samples powered by join plugin when they come up from the July of 2015 to last month. As you can see from this figure, until the July of 2016, the number of malwares is quite small, but there's a big jump at the first quarter of 2016, followed by another hike in the second quarter. From then on, the number of new malwares that powered by join plugin is increased gradually by 100 or 200 per month. But you can clearly see the trend, how this technology has been widely abused by malware. So you may ask, why attackers are so interested in this new technology? Based on our observation, we think there are 3 reasons. The first one is that with the join plugin technology, once the attacker can trick users to install one of its malware on their device, they can install new malware or update the existing malware without rooting the phone and also without users' interaction. So because the attacker will put the malicious code into an individual or separate APK file and load it as a plugin at the runtime. To update it, it only just need to download the new APK file from a remote server and replace the old one on the file system. There's no permission needed. There's no user confirmation needed. By doing this, attackers significantly reduce the chance to be detected by users when they update their malware. The second reason is that this technology can help the attackers to bypass static detections, because all of the malicious code is inside the plugin file. can be downloaded at a runtime. And so if we just look into the host app, the malicious host app, it barely contains nothing, because the only task is to use the plugin technology to load the malicious plugin. So without dynamically inspect the malware, it is hard to find evidence of the malicious behavior. The third reason is that along with the development of a detection technique, the chance of repackaging a popular app becomes smaller and smaller. Repackaging is the most widely used technique to do the phishing attack. So plugin technology can be used as an alternative way to do the phishing attack without repackaging the original APK file. So the attacker can create a malicious host file and use the plugin technology to load the authenticated victim app dynamically without repackaging it. And by doing this, they can put the malicious code in another plugin or in the host app to steal user's input and other credentials information. The first discovered malware family that utilized the joint plugin is called Plugin Phantom. We discovered it at November of 2016 and published a blog with our analysis of the samples. It's also been reprinted in other medium as well. The behavior of the plugin Phantom is quite common, including taking a picture, capturing the screenshot, and intercepting the SMS message. The uniqueness of this malware is that it modularized each malicious functionalities as a plugin, as each individual APK file, and leverage the joint plugin library to load it at the runtime. So this figure here shows the structure of the malware. You can see here that it contains 9 plugins. It's 9 individual APK files, and like the contact plugin, which contains the code to steal users' contact information. And also they have a plugin called Update, which will update, which download the latest version of the APK file from a remote server and update each modules. Another scenario to abuse plugin technology is to phish on the authenticated victim app. The dual Twitter malware is one of the samples targeting our authenticated Twitter app. This malware is mostly downloaded by users who want to log in multiple Twitter accounts, but definitely at a price. Once the user launch this dual Twitter malware, the malware will load the authenticated Twitter APK file as a plugin, and then once the user try to log in to the Twitter, this malware will steal users' input and other credential information. We have also found a similar malware targeting our authenticated Instagram app, and we believe that more and more social media apps will become the victim of this new type of attack. So how can we find a solution to help those authenticated victim app? There are several solutions we can pursue. First is that we can block the usage of plugin technology, which is not feasible due to the large number of users who rely on this technology in their daily life. The second one is we can modify the Android system, like Google to do it, and like the system to support the plugin technology, so that the user won't take risks to download the untrusted third-party host app, like the dual Twitter malware. But this is doable, but it requires longer time for the Google to develop it, and that is not doable in a short period of time. And our solution is that we just want to give an opt-out option for the legitimate apps to let them detect whether they are running in the virtual environment as a plugin or not, and let them to decide whether they want to be launched as a plugin or not. So our solution, the plugin killer, is a library. It's a lightweight library that provides those opt-out solutions. Basically, our library implemented multiple mechanisms to detect whether current running environment is virtual or not. and without modifying the existing system, and it's compatible to all of the Android versions. To use our library, for example, if the Twitter app, they do not want to be the victim of the dual Twitter malware, they can import our library and put these 3 lines of code at the beginning of their main activity. Basically, these 3 lines of code just invoke 2 functions which is implemented in our library. The first one is to detect whether current running environment is virtual or not. The second is to terminate the app or alert users. And this is a similar technique if you are familiar with the cybersecurity. It's called frame busting. So if for any web application, if it does not want to be loaded in the iframe page in another untrusted page, it can put a piece of JavaScript code at the beginning of their page and detect whether it's an iframe page or not, and then it can bust out from the iframe to the mainframe. So it's kind of a similar idea for our solution here. So the essential part of our solution is how to detect the virtual environment. That's the key part of our contribution. We listed 4 directions that we can pursue, and for each direction there's multiple ways to detect the virtual environment. But I will only just explain a little bit of this, but due to the time limitation. But you will get the basic idea here. The first direction is to detect a mismatch in the plugin's manifest file. For example, if we define a service called Black Hat Demo in the manifest file and with no permissions declared, then if we launch this APK file as a plugin in the host app powered by Zheng plugin, when we check the service name, we will get the name of the stop activity, as we just explained, because the replacement made by the Zheng plugin instead of the original service name. And if we can also check the number of permissions granted but not declared by us. We will find 125 of this. This is because the host app, they need to support any plugin file, which means that they declared nearly all of the Android permissions, but they cannot drop them at the runtime. So all of the permissions is there. So our library distinguish those differences between the runtime behavior and the declaration in the manifest file to detect the virtual environment. Another direction could be check the runtime information. For example, if our plugin APK file will running in a single process, but once we load it as a plugin into the host app, we can observe 2 processes running with the same UID, one for the host app, one for the plugin, and and we can use this as an indicator to detect the virtual environment. Another example could be the data directory, which is assigned by the system for each app to store the persisted data, and usually the folder is in data folder followed by the package name. But in the Zheng plugin case, the system only assign the directory for the host app, and all of the plugin file need to share the same folder. So Zheng plugin will create a subdirectory for each plugin file. But you can see that if we check the data directory at the runtime, it should behave completely different than the normal case. And that can be used as an indicator here. We can also detect the app component's behavior. For example, remember that the host app predefined some stub components, but they only have a limited numbers. For example, the Zheng plugin will declare 10 services and 10 activities, but if we launch more than 10, the Zheng plugin does not have any stop ones to replace, and it will lead to a failure. And we can use it as the detection rule. A more advanced example could be used static broadcast receiver. So drone plugin need to convert all of the static defined broadcast receiver to the dynamic ones. This is because the static receiver is defined in the manifest file, but the plugin file has never been installed, so the system won't notice those static defined receiver. So the drone plugin need to pass the plugin APK file and get those static defined receiver and converted and registered them in a dynamic way. So we can come up with a case like we define a static receiver and unregistered all of the dynamic ones. So in normal case, the static receiver is still alive, but in the drone plugin case, all of the receiver is gone. So all we can do is we can just need to send a broadcaster to see whether it can be intercepted or not to detect the virtual environment. Another case it could be I want to share is to change the component property at the runtime. For example, if we define a broadcast receiver, but we set the enable property of it as false. And this means this component will be initialized by the system and will not be initialized by the system at the installation time. But Android system allows us to re-enable it at the runtime. But in the drone plugin case or in the virtual environment case, this enable doesn't work due to the limitation of the plugin technology. And so what I just discussed is a small portion of test cases that can be used to detect the virtual environment. Of course, you can come up with your own ones to detect the virtual environment. We open sourced our library in GitHub. You can find a link at the end of this presentation. We are also glad if you can share your thought with us, and then we can add more test cases to detect the virtual environment into our library, and we can help more the legitimate apps to be not the victim of those new type of attack. And we want to evaluate our library by creating a demo app, and which uses our plugin killer library, and we launch the APK file as a plugin in different virtual environment to test whether it works or not. So for attackers, if they want to use plugin technology to power their malware, they can either get a library like the drone plugin or reverse engineering the existing benign host app as I listed here. Those apps are popular, but they are benign and legitimate. The reason I put here is that their idea to implement the plugin technology can be borrowed by the attackers. So we just want to make sure our library can detect all of the different environment. There's one thing I want to emphasize here is that there's no standard way to implement a plugin technology. Different developers can come up a different way to implement this, and they have a different mechanism as well. So this figure here shows our detection result. So our library can detect all of the virtual environment. So even though the attacker may borrow the existing host app design or come up with their own design, it's highly possible that we can find a way, at least the certain test cases can be used to detect the virtual environment. So it means that for any legitimate mobile app, if it does not want to be launched as a plugin, they can use our library and to make it work. So that's the end at the end of my presentation. I hope you can get three things. The first is the Android plugin technology. You have a basic idea of what it is and how to implement it. And also, you know that this amazing technology has been abused by the malware already. If you are using the similar host app, like the dual Twitter app, be sure to check the host app first. Do not be the victim of those new type of attack. And if you own your own mobile app, and you do not want it to launch as a plugin by any untrusted third-party host app, you can use our library to protect your own app. So here's a link for our library, and also we believe that the plugin technology completely changed the security landscape of the mobile security, especially for the Android security. There's a lot of issue here. What our research is only the first step. We are looking for any collaborations to follow up research related to the Android plugin technology. If you are interested in this and want to continue your research, please feel free to share your thought with us. We can come up with something new. And so, yeah, that is the end of the presentation. Again, thank you for coming my session. Thanks. If you have any questions, please feel free to ask.
Okay, so you mentioned now you see more and more plugin malware.
Yes.
So do you have a number for right now how many percentage is plugin malware account overall enjoy malware?
So you mean how many percentage of the
Plugin malware account overall enjoy malware?
Oh, that's a yeah, we can measure it in our internal database, but currently I don't have a number. It's not a half right now, probably just one third, but you can clearly see the trend here, because the advantage to use those plugin technology, I think more and more attacker will convert from the normal ones to here. Like the plugin Phantom, remember that malware I just introduced here? This malware originally is the normal malware. We discovered half a year ago. Then we found that it's completely changed. It's completely changed their malware structure to use the power of the plugin technology. So I hope this can answer your question. Thanks.
The behavior in MDNs, I'm not sure, you didn't mention it.
Pardon?
The behavior of all these types of plugins in phones that you have MDN protection. So do you have the same percentages, number of people that are being protected?
Oh no, we don't have the number here, but we can just because all of the data is in our internal database. We can definitely measure that.
What is the percentages of people that do have MDNs installed?
You mean what the percentage of the people who already installed the host app?
MDN, but organizational.
Oh. Actually, I don't know the number, but we can talk about. Huh?
You experience this type of behavior in organizational phones. If you have MDN installed in your phone, right? So this type of plugin, how does it work?
How does it work in?
The plugin killer, right?
Oh, that's the plugin killer. But currently, we tested for all of the Android versions on the different virtual environments. It works. It can detect all of them. So yeah, I think currently we are confident to say if you install if you use our library, you can definitely detect the virtual environment. Yeah. Okay, thanks. What do you mean by the question is what is possible to use our library, right? Oh yeah, that is the good question. The question I rephrase here is that our library cannot distinguish the benign virtual environment or the malicious environment. So basically, our library just currently we can only decide whether it's a virtual environment or not. For the legitimate app here, we can also detect them. So as well, it counts as a false positive. In order to make it work, our solution is the host app, like the parallel space, they need to communicate with the third-party app, such as the Twitter. They need to collaborate to set up some authentication mechanism. So, which means that the Twitter app allows the parallel space to launch it as a plugin, and we can add this new part to our library. If it passes the authentication, it means that even though it's a virtual environment, it's fine to launch. So I hope this answer your question here.
Actually, I was also asking standard Android versus plugin environment, whether you can, whether there are any cases where you detect standard Android as a plugin.
Can you make it louder? Cannot hear.
Standard Android environment, are there any cases where you detect that as a plugin environment?
Okay, no. Because our test base is the behavior of the normal environment. If we launch it, we see any of the abnormal environment. That basically is the virtual environment if the system performed correctly. Yeah. So currently there's no false positive things here. Okay. Thanks. Okay, no more questions. Thanks you for coming to my session.